Hey guys, this is Alex from Canyon Academy, and I'm going to go over some properties of resonance structures with you. I want to mainly go over how to draw the resonance structures, decide which one's the major contributor and the minor contributor, and then from there, I'd like to talk about the stability and properties. So first off, we're going to just go ahead and draw a couple of these resonance structures. So if we were given this molecule above, we would want to come up with some of the alternate forms that it would exist in. And the game we play in this while doing resonance is we go from lone pairs to pi bonds and back. We can also go from pi bond to pi bond and lone pair from lone pair. So we can go back and forth from the same thing. Okay. Now, if you don't know what a pi bond is, it's just part of the double bond in a structure. So let's say if I drew out a simple double bonded structure here, if I drew the two H's at the side of this ethylene molecule because of that double bond. Now one of these bonds is called a sigma bond. That's the one that's from the single bond. That's made up of the sp2 hybridization. And the other one is the pi bond. That's made of an overlap of p orbitals. And that is the one that will be moving back and forth. We don't want to break up a sigma bond at all. If we break one of these, we end up destroying the structure. So we can only go from pi bond to pi bond and pi bond to lone pair. Now let's jump into our first problem. So let's draw out our lone pairs so we know what we're working with, because those are one of the players of this game. So let's put these in. We know that a negatively charged oxygen has a state of 3 lone pairs, and a double bonded oxygen has 2 lone pairs. So playing the game, we'll find a couple candidates. Let's go over a couple things that you wouldn't want to do. So if I wanted to move this lone pair here, maybe I want to turn this bond into a triple bond. Why that isn't a valid move is because then I have 3, or actually a total of 5 bonds in this, because I would create a new bond. Let me make that out in red. So if I wanted to do this move, I'd have to make another move to get rid of one of those bonds. And the only thing I can move is one of those pi bonds. And if no matter which side I move these pi bonds on, if I want to move it there or there, I would still have a total of 5. So I can't move that at all, that lone pair, or any of the lone pairs on this oxygen. Now, if I wanted to try moving the pi bond alone, maybe I wanted trying to move it to this side, I would still have a total of 4 bonds, but this oxygen would be in a weird state where it has way too many lone pairs, and it would have to actually be bumped up to a strange orbital, the d orbital. So if I wanted to move that bond there, and get rid of the original that I highlighted in red, it would give me a weird stated oxygen. So I can't do that movement either, but there is somewhere else that we can move that double bond to. Let me just redraw a couple of these, and I can actually decide to kick this off to the oxygen. This is a valid move, but it would split up a charge, meaning that this oxygen will have 3 lone pairs and have a negative charge. And if I were getting a new charge, that means we're splitting a neutral, most likely, because we're keeping this negative charge up here. So anyhow, let me draw out that, because it's still a valid move. It would just be a minor contributor. So we have the same skeleton of signal bonds. That's usually kept the same because we never break them. Then we put in our elements, and we kicked off one of the lone pairs originally in that pi bond, because remember, these bonds are made up of 2 electrons. So if I could also just draw it out like this, so that's being moved over here. Now this is a negative charge But it's important to note that we don't replace a hydrogen here. We move that bond, so this carbon is now it now has another charge, and this oxygen at the end still has negative. So here what we did was we basically split off and made a new charge from the original compound. Usually you don't want to do that, but it is technically another contributor. But let's keep going. Maybe we can come up with one more structure. It's always be careful to note that you're making the same molecule. So if I did the move to go back, I would have to take note and make sure that I didn't count it twice. But another move now that I can do is I can move this pair of electrons on this oxygen and make a pi bond to get rid of that positive charge, because usually we want to go electrons to follow a positive charge. So again, I'll redraw this out with the same sigma bond skeleton. But now I moved and created a new bond here, a pi bond. I still have all the same electrons on this oxygen for a total of 3 lone pairs, so it's still a negatively charged state. This lost its charge, but now it's just neutral. So that made up for the breaking up that we did earlier. So these three would all be resonance structures of each other. Now to decide the major contributor, we use these rules over here on the side that I use the acronym ROBES to describe. And they're in order of priority of the most important things that decide a major contributor. So the first thing that decides a major contributor is the octets being full. So we want all these elements to have a total of 8 electrons in their valence. So if we can count those off, if we wanted to, so let me get rid of this real quick. So let's start with this bottom left one. This oxygen here has a total of 6 electrons in lone pairs, and it has 1 bond. So remember, those bonds are made up of 2 electrons. So it has a total of 8 in its valence. So this is a complete octet. The other oxygen does as well. This one in the center, however, is missing 2 electrons because positively charged carbon with 3 bonds has no lone pair, so it only has 6. So this one has an incomplete octet in this spot right here. So this one already, by our major priorities, fallen behind the rest. No octet. The other ones we can double check. We already said that a negatively charged oxygen has a full octet, so this is valid, and the other oxygen in the other molecule is valid. A normal oxygen in neutral charge also has 8 electrons in its valence shell, and this carbon has 4 bonds, so it actually as well has a full octet, because for each bond you have 2 electrons. 8 times 2 gives us, 4 times 2 gives us 8. As for the other one, it's basically the same thing as that molecule, just flipped around. So we can keep going and to count bonds, electronegativity, and separation, but because this is just the mirror image, 1 and 2 over here is just the mirror image of each other, we know that they're both major contributors because they're just the same thing. And they also have complete octets, and they would have the same bonds, electronegativity, and separation.